Hello, how are y'all doing today?
Good, how are you?
Doing okay. I just realized though I should turn the volume up so I can hear you better if you unmute because that was on the quiet side here. So yeah, thank you. I loved it. Hey, how about this? I'll just do the normal thing because why not? And then we'll just see where we get to. Desktop one, good share. Lovely. Um, so trying to draw your attention to things that matter today and in the near future. First, just hey, there's this week 2 lab group survey. Admittedly, in the first week, there's a couple of people who are saying, yeah, and in the second week, there's been less of that, and someone was able to move, and I thank you for being able to move. That really helped some folks out. Thank you. And ultimately, we're with groups that I think are fine. Uh, if you got complaints, hey, you got the survey that can tell me those complaints. Or if you really like your current group, you can tell me that. Also works nicely. The key is I want it to be such that as we move forward, the groups are ones that either you love or are very tolerant of, maybe that's not a love, but tolerant of, or if there's something that's awkward or challenging, let me know and we'll mix things up. Second thing I want to mention is today we just finished up office hours in the afternoon. It's like half an hour. But in the morning time, I talked to a couple people, and then in the afternoon, no one actually showed up from this class. And so, well, okay, cool. That's a good sign. Um, but right following class, even though it is a Thursday, and normally we would have office hours for like half an hour after class, I'm not able to do that today because of an appointment where I have to get in the car and drive and be somewhere right quick. And if I look at the syllabus, I'm going to click my way into that. I'm spotting a couple things are maybe important. One of them is, hey, July 2. That's sort of like a date that matters. July 2 is when exam one needs to be turned in. And that was live as of Tuesday afternoon late. So about 5 o'clock, I guess. So that you had like 7 hours plus another 24. And then you will have an additional few hours to finish up. Basically, by 11:59 p.m. tonight is when you need to be done with exam two. I mean, exam one. Sorry about that. And most folks that I've talked to who haven't quite taken the test yet were saying, okay, I can get it done, but I always recommend starting with at least an hour extra because if technical difficulties happen, like the internet isn't perfect near you, having the ability to sort of like start over or let me know and let me try and resolve things at this end is a good idea. So that's it in terms of administrative things I wanted to mention. Do any of you have administrative questions that you'd like to ask related to the exam? Not about any particular questions, because you don't want to you know, ask about something that's on the test. But, if you got any administrative questions or ask things in a general way, that's a good idea for now. Okay. Then how about subject matter questions? Last time in class yesterday, we talked about regression, fitting a straight line through data. And I said, oh, yeah, it's least squares is what Gauss would have called it, or regression to mediocrity is what Francis Galton called it. But essentially, it's how would you draw a straight line through data in the lab yesterday that you should have just turned in. It's not too hard to do that. The calculus solution is automagic. A computer will do that for you, but knowing the logic behind it is a good call. And we saw in the lab yesterday, even if there's a curved relationship between X and Y, by perhaps taking a transformation, re-expressing the X variable, or maybe re-expressing the Y variable, we can take what was a curved scatter plot and straighten it out. And if you have a straight scatter plot, you can use a regression. That's why I think engineers, y'all are the only group out there that still uses that funny logarithmic scale graph paper. I don't know if you've ever had to buy it in person or live, so like real humans on real paper. But that logarithmic scale is something that you don't find in all the different disciplines. And having something which is on a log scale on the x-axis but not on the y, or the y-axis but not on the x, or log scale on both, sometimes is really helpful. Those transformations can create linearity and thus allow us to use least squares comfortably, where in the original units we might not have been so happy. So, with all that in mind, any questions related to chapter 3, section 3, or 3, 4? Okay, then. So, what I want to do is to sort of tip my hat and let you know. Today, I want to talk about all of chapter 4. It seems as though chapter 1 took a couple days, 2 took a couple days, 3, 2 days. Chapter 4, I want to do that all in one day, and I have the feeling it'll be good. And then we're going to slow down a little bit in chapter 5, where the material is, I won't say more subtle, but more prone to typical student confusion. And so it's not inherently confusing, but sometimes going slow is really helpful. In chapter 4, most students are like, cool, cool, okay, fine, move on. In chapter 4, sections 1, 2, and 3, chapter 4, section 4, we're just approaching it from a slightly different point of view. And the lab activity is emphasizing chapter 4, section 2 and 4.4. And so the areas where 4.4 are a little challenging, you're going to confront head on in the lab. So unless y'all have a question, and unmute and tell me what the question is. Actually, hold on. Let me open up a chat window. So if you do have a question in the chat, I can see it. And then also, why not? I'll put the participants here in case one of you unmutes. I'll then see that also. Okay, so I should be good. Let's do it. In chapter 4, section 1 and 2, actually just 4, section 2, what we really are talking about is what if you're sampling from a population of individuals. Now, I'm not going to really fuss about the distinction of a finite versus infinite population. A finite population being like, oh, the literal number of people who work at Cal Poly, that's, 2,300 or so. There's a finite population. There's literal individuals out there. Or maybe an infinite population, which could correspond to if you've ever gone over to the food science department and taken the chocolate class or the meat processing class, you might have sort of had someone walk you by the extruder, which I think is sort of fun. I call it the Cheeto maker, and you based on a number of dials and settings and things you could put in a hopper over here and a hopper over here, you could end up making freeze-dried oatmeal or a Cheeto or shoot something that's slimy and worm-like. So there's a lot of things you can do with this machine. And let's just consider, what if I set the dial for the humidity level, okay, in the resulting product, and I set the dial for the amount of water that goes into it, and the dial for the amount of dried product that goes into it. I set those three dials, and I just turn the machine on and crank it out. Could I keep making these Cheetos? Because you literally can make a Cheeto with this thing. Could I keep making these over and over and over again? And is there essentially a process where I could produce an infinite population of Cheetos as long as I keep refilling the machine and it doesn't break, and maybe a couple other things that are, I guess, technically unrealistic, but in a concept, we could think about a process as producing the possible data values that we could see. We're talking about where do you get your data, okay? So in chapter 4, section 2, we're going to start by talking about sampling, okay? And so let's write that up there, sampling. And I'm going to focus on the finite population context. And this is going to be setting you up for material that we're going to see in chapter 5. And so I want to be a little on the careful side. If we have a population of n individuals, and I'm going to use capital N as the number of individuals, with a population mean of mu and a population standard deviation of sigma. Basically, think all the Cal Poly employees right there. There's a collection of individual Poly employees. And if you want to know characteristics of them, like literally the distance to campus that they live, and we're going to measure that in minutes because we're in California. I could take a sample of, because I don't know all 2,300 individuals in the population, but if I take a sample of the individuals, literally n of the capital N individuals, okay, that is going to be my way of collecting data. And I want to define a simple random sample. Oh, man. Let's go with that. And let's pick a new color because I want to. A simple random sample. SRS. Basically, think the gold standard of possible samples that I could take. My simple random sample is one such that each simple random sample is defined as each collection of n of the n individuals is equally likely. Okay, so that's the definition of a simple random sample. Every single possible set of size n is just as likely as every other individual sample of size n. So in this class, there's, I think, currently 47 people enrolled. And if I'm going to take a sample of 5 of the 47 of you, oh, geez, there's rules on combinations and permutations that we'll hit in chapter 5, so we can avoid that for now. Every single group of 5 people of the 47 of you all has to be equally likely to be the sampled group. So that sounds like there's a lot of possible samples. That's what it means to be a simple random sample. Every single individual possibility, it has to be equally likely to every other individual possibility. So let's give you an implication of that. Okay. And I'm due to Zoom issues, I'm going to write really small so I could actually do the writing. I'm running out of space on my screen, even though it's not showing there. But this simple random sample implies each of the n individuals in the population is equally likely to be in the sample. And that meets our sort of conceptual definition of fairness. If every one of the 47 of you is equally likely to be obtained in my sample of 5 of the 47, if every one of you has a 5 in 47 chance of being in my sample, you would say that's fair. No one is being favored and no one being discriminated against in the process of being collected. Okay. Any questions about the simple random sample? Okay. Let's talk about a stratified random sample then. A stratified random sample, the best way I think of thinking about it, is if I take my population out there and think again, all Cal Poly employees, and if I could divide my population into subpopulations, And in this case, I'm going to go with five subpopulations. In each of these subpopulations, in each of these strata of individuals that are in some way similar to each other, we're going to separately sample from within each of the strata. Okay. And so what you're thinking is, let's go with a new color. Let's go with this greenish color. Again, I've got these individuals in the population called faculty, and I've got individuals in the population called um, administration, and there's a group of individuals in um, it's called F and A. Um, Basically, think people who fix things on campus. So, um, what do you want to call those? Maintenance. And then another group would be individuals who are administrative, but they're more secretarial. Okay, so assistant, department secretary, perhaps. Okay, and then in this last category, it's going to be folks who work in food or other things. Okay, so maybe I have more than five strata, really, but conceptually, there's a population which I could say, well, this sort of people will treat one way, that sort of people will treat a different way. And the reason I might very well want to do it is if I want to then take a sample of size N1 from that first group and size N2 from the second group and a size of N3 from the third group, etc. Overall, that sums up to the total sample size of N. If I take a sample such that I'm going to maybe see a greater fraction of the administrators and a smaller fraction of the faculty and a larger fraction of food service workers, that might be desirable. Let me give you a different example to explain why that might be a good thing. Suppose I really want to compare across different majors. So we got like folks in engineering, and then I got folks in science and math, and then liberal arts, and then architecture, then the I guess ag people, and then did I mention architecture? Business, yeah, the College of Business. And within each college, you would want to then have maybe the same sample size, right? The same sample size because I might want to ultimately compare from one college to the next how happy students are with their Cal Poly experience. Because frankly, you might find engineers love the place and ag people love the place, but maybe it's for liberal arts majors, they're like, not what I had imagined. So if you're measuring student satisfaction, you might want to do that such that you have about the same number of people in each of the different strata that you're sampling from. Um, we'll see in a later chapter, chapter 5 or 6, why that would be beneficial. But if I want the same number of people from each of the different colleges, you're thinking architecture. There's only like 12 students in all the whole college. Okay, I exaggerated. There's only 2,000 folks in architecture across the entire university. Okay, less of an exaggeration. But there's like 5,000 engineers every single year that are admitted. It's just ridiculous, the number of engineers compared to architects. And if I saw the same percentage, 5% of engineers were in the sample, that'd be thousands of you. And if there were 5% of architects, that'd be 12. I'm again exaggerating for purposes. If you have the same sample size from each of the different populations you're sampling from each of the different strata, okay, you're going to end up being able to more appropriately compare with precision, the right level of precision, the opinions between the different groups. Okay, so stratified sampling, conceptually, we're just going to sample separately from the different groups. Any questions about that? Okay, let me contrast that with something that some people find sounds similar to stratified. So a couple of you'll say, hey, hold on, how is that different? Ask the follow-up question. We'll get into the difference. I'm going to talk about Cluster sampling. Cluster sampling. It's not stratified sampling. Cluster sampling, and maybe I should go with the quickest explanation from the point of view of y'all. You're required as Cal Poly students, and with rare exceptions, to live in the dorms during your first year. Okay, good, got it. And if we want an opinion of students on the convenience of the dining facility. My bet is folks that live like right nearby might say, oh, yeah, that was pretty convenient. However, if you live further away, you would say, oh, that's less convenient. And a simple random sample of all students who are living in the dorms might be very hard to take. Because to be honest, especially, and I'm going to go with the in-person, now someone knocks on your dorm door, um, we probably really wouldn't do this, but let's suppose people are going to go and literally knock on a door. If you take a fair sample of 100 individuals from the entire population of folks that live in the dorms, and maybe that's about 6,500 right now, of the 6,500 students that live in the dorms, if I'm taking a sample, let's go 200. If I'm going to take 200 over, let's go even 6,650, because that's an easy percentage. If you're going to take a sample of 10% of all students, what I'm going to end up doing is walking and knocking, and then I'm going to sort of have to go up 3 floors and knock again. And then I'm going to have to go up another floor if it's a tower and then knock again. And then I'm to sort of sample everyone. It's going to take a lot of time and effort. Wouldn't it just be frickin' easier to say, okay, I'm going to roll dice and sample one whole dorm floor and knock on every single door of the people on that exact same floor? I'm thinking that's going to save a lot of time. Yeah. Yes, it will. And I just want to let you know that, yes, if you're going to find natural groups that you could collect all of them in one group into your sample, or maybe none of them if they were not lucky enough to have been a sampled dorm floor, you could get a sample of the right level of precision that you want. Again, see the future chapter 5 and 6. You could get the target level of precision even with this method that saves you time. Simple random sample is the gold standard. Stratified is if you want to make sure I can fairly compare groups or I have desired percentage levels in each of the samples. 5% of one group and 12% of another group and only 2% of a very large group should give me a sample that's large enough. Cluster sampling is going to be where it's costing you money to take your sample. And money is one of those limited resources. And because it's a limited resource, it's an optimization problem. And let's get the best outcome, the greatest level of precision, the least bias for the least money. And if instead of walking up and down dorm stairwells or taking the elevator and taking time to do that, if all I need to do is to say, okay, just go to this one floor and knock on every door, I could get a very sizable sample in a lot less time than if I'm taking a simple random sample of that same amount. There may be problems with cluster sampling. There might be, but indeed, it's still something that we could do to save time. Strata, stratified sampling. There, within the different groups you're sampling from, there is some similarity. Cluster sampling, we're just doing it as a matter of convenience, and they sound similar, but literally, the methods that we use, and we're going to see in chapter 6 and 7 that the statistical methods we utilize, we're going to assume always a simple random sample or the equivalent of that. I'm just going to let you know in a later, more advanced stat class, any method we teach you in this class, if you were to use stratified sampling or if you were to have to use cluster sampling, we're going to say, oh, and just here's how you could quickly tweak your formula. Not a big deal. And now's where I put in the plug. for the Stat Department Consulting Service. When you are working away on your senior project or your master's degree or whatever it is, if you need to collect data and do the analysis and you're not collecting the data using a simple random sample, we encourage you to go and talk to the folks who are in the statistical consulting service. They'll give you a free consult and steer you the right direction and say, remember the equation you learned in 312? Here's how we tweak it to correspond to the fact that you used stratified sampling. And you're going to say, okay, I could write that up in Python, or okay, I could do that with the standard software package JMP, or perhaps R if that's your preference. Any questions about sampling, cluster, simple random, stratified?
How do you make sure that your cluster doesn't have a specific bias that would make it not applicable for the larger population?
Okay, great question. You're noting Chapter 4, Section 4, words like bias. How do we make sure that our one particular cluster doesn't bias things? I'm just going to say if every cluster one has a certain chance of appearing in the sample, we're going to sample a whole cluster like a whole dorm floor. If you're sort of saying we want to get information on the students' feelings about food, and you're thinking, well, we happen to have grabbed a floor which is only engineers. I don't think that engineers will necessarily have different opinions about the food than folks of other groups. But your question suggests what if? What if engineers would have a different systematic opinion? I would only rely on, well, we might have sampled a different floor, and it could have been in floor instead of floor with business majors. If every floor has a probability of appearing in the sample, such that no individual floors have a chance of zero, we can doctor our, shoot, wrong word. We can adjust the results ex post facto to correspond to, yeah, we had a bit of a possible bias, and so we're going to say there's more variability than we had otherwise would have had if it had been a simple random sample. So, John, I'm trying to be vague in the terminology. We could be more specific in office hours if you like. The real issue is we can adjust for that. And the key is you can't exclude any particular floors because that itself is where the bias is non-recoverable. Did I answer your question, John?
Yes.
Did you say yes or sort of? I didn't quite hear.
I said yes.
Okay, good enough. And this is a great question for, if you're going to go and collect a sample of individuals, and if you're worried about it, talk to the stat consultant and we will steer you the right direction. It's just that it's beyond the scope of this class to treat in a serious way, other than saying it's something to watch out for, ask, and we'll reward you later with a question, an equation that fixes the problem. This method, the methods we're going to learn in this class don't quite cover it, but it still will provide you the tools that will allow you to say, oh, well, we're not going to use the one kind of screwdriver. We're going to give you a fancy one. We'll give you a Torx later on. Right now, you're dealing with just Phillips. Okay. Other questions related to sampling? Okay, so let's talk about random assignment. That's a next little section. And that's more in the context of an experiment. I think with sampling, what we say is, aha, we know there's natural variability in people's opinions about maybe the food services or how close they are to the dorms or convenient they are, maybe is how I phrased it. In the context of an experiment, we should randomly assign individuals to treatments, treat them different ways. And I'm gonna sort of suggest okay, so here's an experiment that I saw some folks in kinesiology do about 20 years ago. There's a grad student coming through. His name was Steve, not me, but some other guy named Steve. and he was a bicyclist, and he wanted to measure the peak amount of work produced by a cyclist when well in various different conditions, but importantly, different gear ratios. And so gear ratio, what's that? Like 53, we call that little, what do you call the little things that stick out in a gear?
T.
Teeth. Okay, perfect. We'll use the term teeth. Love it. 53 teeth on the sprocket, okay, and then 23 on the cog, the big one on the front that you crank, and then the one in the back, or maybe it's the other way around, but one's called a sprocket, one's called a cog. You're probably better than me at this. Some of you even ride bikes, I bet you, and you know the terms. But essentially, 53 teeth on the big one and 23 in the small, it's going to get you a different amount of work, perhaps, than if you have 55 on the front and 22 on the back, or 21 on the back. So the gear ratio, the ratio of teeth in the sprocket to teeth in the cog, you could convert that into a number like, 2.3 or 2.5. But let's just say there's different gear ratios that Steve wants to compare. And so there's one variable here that's called gear ratio, GR. Okay. And suppose there's 5 different levels, and we'll call them low, very low, medium, high, and very high. Okay. Very low gear ratio means it's going to be really easy to accelerate. Very high gear ratio, it's really tough to accelerate from a stopped position. But you'd want to be in the very highest gear ratio if you've already gotten up to speed and you're wanting to maintain the speed. The work is better in that range. Okay, so let's talk about random assignment. We've got these different gear ratios. Well, the problem is, if I give one cyclist, and he recruited people from the cycling team to participate in this, if I say to one cyclist, oh, you just use the very low gear ratio, and another cyclist gets the very high gear ratio, somehow not fair, because maybe the one cyclist in the very low gear ratio is just a weaker individual than the person with the very high gear ratio. You'd want to naturally try every single individual cyclist at every one of the gear ratios. So individual cyclist. And so I'll call it cyclist 1, cyclist 2, 3, IV for 4, V for 5, VI, VII. Let's suppose there's 7 cyclists because I ran out of room. So across my situation here, I've got these 7 different cyclists, each trying these 5 different gear ratios. We're essentially blocking the different gear ratios against the cyclists. Literally, because there would be excess variability if we said to each cyclist, you give me one of the gear ratios and we'll just measure the peak work that you produce. And shoot, we got enough cyclists out there we could do it that way. But I'm thinking, because some cyclists are better than others, yeah, are stronger than others, have better endurance, whatever it is, there are different peak amounts of work that they could produce. There's natural variability across the cyclists that we would want to naturally account for when analyzing the impact of gear ratio. So we're going to randomly assign individuals to treatments. Okay. The individual cyclists are, in this case, assigned to all the treatments. And in this case, we're blocking. We could actually do it other ways as well. Let's give you maybe another possible experiment. And this is, how do I want to do this? Okay. Yeah. Okay, so here's something I saw. And if you're in materials, you might have heard of these things, and please correct me if what I'm saying is really silly. But we've got 2 different numbers out there, which are corresponding to the mix rates of 2 metals in an alloy. We know that X1 plus X2 has to be 100% of the ultimate metal that's produced. And X1, I'm going to say that that's equal to 60%, 65%, or 70%. Okay. X2 then has to be, well, 40%, 35, or 30. And we're ultimately looking for how hard is the resulting alloy going to be. And there's three different treatments. Okay, so 60, 65, and 70 are the different percentage of the first material. And again, there's well, a situation where I've got these three different levels. Maybe there's also three different temperatures that we're mixing at. There's low, medium, and high. Across these three different mixing rates and three different temperatures, there's 9 different possible treatment combinations. And you're imagining, well, there's medium low and there's medium high and there's very low and very high. And we could go with, 55 and 62 and a half. We're not really limited to these situations, but suppose I say, based on material that I took in another class that would naturally follow this one, Stat 323 or whatever the hell it's going to be named in semesters, uh, we might very well say, yeah, there are other possible mixing rates and other possible temperatures that I could choose. But for now, I'm saying these are the 9 I care about. If this is the collection of 9 that I care about, I might say to myself, okay, cool. I could do this. I could do this. The problem is, what order do I do these 9 treatments in? That's sort of a tough one, because maybe order also is going to play a role here. I would imagine that if you're giving the students this task for their master's degree, you say, well, you're going to mix it at 60% at a medium temperature, and then the next time you're going to mix it at 65 at a high temperature, you might see a secular trend that the hardness might just get better across the 9 different trial temperature mixing rate combinations. And if there's going to be that secular trend across the 9, you would not want the trend to be biased, like by doing all the 60% mixing rate earlier, then 65 next, then 70 in the third slot. You don't want to do them all, okay, in order according to either the rows or the columns. Because then you couldn't really tell, is it because we're just getting better at doing the job, or is it because we're using the medium temperature as opposed to the high? If there's a trend upwards in the quality or downwards in the hardness or whatever it is that you're measuring across the 9 different units, you want to randomly assign the treatment to each of these 9 treatments to an order, or perhaps given ordering that is such that I guess we have the 3 that are lowest in not any one location, not any one row. Maybe the 3 lowest have to be in 3 different rows, and 3 different columns. So the 3 first, so the 3, and I guess I could be more careful than this, but let's just go with the first 3. 1, 2, and 3. We should have them in different rows and different columns. So I guess if I have the low temperature 65 mixing rate as the first thing that I do, I can't choose in the same row or the same column for the second or the third. So let's go up here. The second might be there, which means the third has to be in that third slot, that third only available slot. Again, if you're saying rows and columns are not allowed to be repeated in a group of 3, we're going to switch gears from the first day to the second day. I've got 4, 5, and 6. And I'm thinking, shoot, again, I don't want the same rows or columns to be obtained. So how about we'll go with 6 and then 4 and 5. That's not necessarily the right way to do it, but that could be randomly chosen. And let's go with a third different group, and let's go 7, 8, and 9. And it looks like they have to be in a diagonal. And I'm not saying there's a right way or a wrong way to do it, but if I go with 7, 8, and 9, that would seem to be a good way to go. Okay. Whew. Okay, so good enough? Try to make sure that you take every treatment combination and do it the same number of times. And if you think there might be a trend, make sure you block across those trends in such a way that you take advantage of that you can then spot the impact of a blocking variable over time. Any questions on that? Okay, so let's move on into chapter 4, section 4. And this is the one that I think is on the subtle side. And so I'm going to start to use terminology and speak like a statistician would speak. You're thinking, you haven't been doing that already? We're using terminology in the bulk of this book where it's pretty much straightforward. Oh, like the average X bar or the standard deviation S. We're going to speak in more general terms here. If you have a population that you're sampling from, so here's your population, and there are characteristics in the population that you care about, theta, which theta could literally be a mu, maybe a sigma squared. There are other things you might care about in a population that you're sampling from, not just a mean and a standard deviation. You could talk about kurtosis, which is sort of a goofy measure of something, how skewed it is, if you will. Skewness is the third. Kurtosis is how heavy-tailed versus, central it is. There's this population number out there, and just think the average, or perhaps think the standard deviation. There's some characteristic that I will call theta. Okay. And if I take a sample, and again, think a fair and representative sample, a simple random sample of size n, that set of data should give me a theta hat. So literally, if I want to know a mean of a population, maybe the corresponding theta hat would be something like X bar, the sample average. Because yeah, let's use the sample average to estimate the population mean. If you take a sample in a fair way, that should be a good way to go. And the lab today sort of explores this. We'll see it in a later chapter as well. And you already even saw this in some way in an earlier lab remember when we were talking about estimating the standard deviation with the sample standard deviation, but you didn't have n-1 in the denominator? Well, we're coming up with a theta hat, an n denominator standard deviation. And then we tried a different theta hat. What if you had n-1 as the denominator in the standard deviation estimate? Which one would be doing a better job? Which one is doing a better job? So there's some number out there that theta is really the population truth. Theta is the population truth that we would like to know. Theta hat is our estimator. So we're going to estimate an unknown value. And this is where it gets a little bit dicey because you have to sort of know about the population to talk about how well your estimator is going to do. But we'll talk about the ideas conceptually for now. And then after we know a little bit more about probability, we'll be more specific. I'm just going to say that there is an expected value of your estimator. So there is an average of the sample averages. There is an average of the standard deviations I could get from a sample. So for any given sample, I'm going to get a theta hat, and I could just average over all of the possible theta hats. And if I want to subtract from that the truth, okay, that difference there, we'll call that the bias of theta hat. So if theta hat on average is not where theta is, you would say your estimator is biased. And that's what John was asking about earlier. Hey, what if we had a situation where like one whole dorm floor had a particular opinion? If we're highly likely, more likely to include that dorm floor in the sample, that might bias upwards, yeah, the estimator of how people are satisfied with the dining on campus. So how far off are we on average? That's the bias. There's another number that is sort of important to consider, and that is the variance of theta hat. Okay. Yeah, literally the variance of theta hat, or maybe I guess the standard deviation of no, let's talk about the standard deviation of theta hat instead of the variance of theta hat. There's two ways of writing one is the variance, and then if we take a root, it's the standard deviation. And I guess you want this to be low. You would also want that other thing to be low. You want both of these terms to be small. Okay, so let's turn that reminder off. Yeah, dismiss it. So you want both of these numbers to be small, and maybe we could get them both to be small simultaneously, but I don't know. We'll have to actually go a little bit deeper. Ideally, you want both small, but there are some situations where you might prefer a biased estimator, and the real reason is maybe what we care about is sort of variance. Yeah, you want small, and bias, you want that to be like 0. But how about this term? The mean square error. ERROR, the mean square error. The expected value of theta minus theta hat squared. Or I could write it as the expected value of theta hat minus theta. And it's sort of, let's work from the inside out and consider what we're really meaning. For any individual sample that you take, you're going to get a theta hat. Is it exactly at theta? I guess it's possible that the sample mean will be exactly where the population mean is. It's possible that the sample standard deviation would be exactly where the population standard deviation is, in which case that yellow underlined term inside the middle is going to be 0. But if it's not 0, or even if it is 0, we're going to square it. And then we're going to find, averaging over all possible samples, how far away what we're using as an estimate is from the number we're trying to estimate. Now, our book doesn't sort of emphasize this in the way that I love as more of a mathematical person, but I'm going to say, yeah, you know what? We can piece this out, this mean square error, out as the bias squared of theta hat plus then the variance of theta hat. And so you want the mean square error to be small. So you would, of course, want both the bias to be small, and then the bias squared would also be small. Oh, I'm just looking at this. Hold on. That is a little bit hard to read. Okay, so let's fix it up. The bias of theta hat. Okay. The bias squared of theta hat plus the variance is what we want to minimize. So you're going to minimize this. And that suggests that maybe an unbiased theta hat is great, but if you get a more precise estimator out there that's biased, it would be better. So let's consider biased versus unbiased. I guess if the distribution of the possible theta hats is very wide around theta, so the possible theta hats is spread right around theta, this would be unbiased. And then I guess same idea here, but notice that it's narrower. This is also unbiased, but it is more precise. Here in this second graph, it looks as though the variance would be smaller. Both have 0 bias. You'd prefer the estimator with the smaller variance, the greater level of precision. Oh, man. Okay, so. Okay, and so I'm going to quick screenshot there. Okay. And any question about that so far? Okay, so I'm going to quickly get to the last page. The last concept is, what if you are comparing two different possible estimators? One is an unbiased So theta is right there, and the possible theta hats are here. But it's got a big variance. Would you prefer a very precise but never right? Okay, so theta hat here, or theta is there. Here's the distribution of the theta hats. Let me yeah, so here's, I apologize, theta. I meant to write theta here. And so let's erase that. So typically what we have here in this second graph is right there is your expected value of theta hat. We're always wrong, but we're always really close here. The bias is small versus here, the bias is 0, but the variance here is tiny compared to the variance here, which is huge. What we're saying is essentially, maybe you prefer the second case where how far off are you typically? Pretty darn close. How far off are you here? You're rarely going to be close. So in a context like this, you would go for maybe the biased, smaller variance estimator. Even though the first one has a bias of 0, the variance is huge, and that overweighs the benefit of the lack of bias. Good place to stop because it is 5 o'clock, actually 5:02. I'm sorry about that. So I'm going to sort of stop this now, and I have to be out the door in about 5 minutes. And so I'm going to sort of stop the share. And if you have any quick questions, now is the time to ask. Otherwise, I'm going to have to shut it down. Oh, and by the way, it will take an extra hour or two for me to post the video to tonight's class because, again, I'm going to be gone for a period of time. As soon as I get the link, I will make it live, but that won't be immediate. Okay, I'm going to stop the recording. We'll see you all soon. Bye-bye.